I'm Frank, this is Payman, this is 340. We're going to talk about machine learning and data mining. In particular, we're going to talk about deep learning, and we'll try to keep the buzzwords to a minimum. Last time we sort of finished up with modern MDS methods, talked about isomap, where we ran MDS on geodesic existences, basically discovering first a manifold and then unrolling it. We talked about T-SNE, we talked about Word2Vec, in particular its SIBO form, which gave us a way to embed words into some sort of real valued high dimensional feature space. And we gave a little bit of an example of this here. This is skipgram, but this is the same as SIBO, basically. It doesn't really matter. Train on a large corpus, and you make a 300 dimensional feature vector for every word. And when you embed France and Paris, and you compute the vector relating France and Paris, and you start with the embedding for Italy, and you add the same vector, you get Rome. This is what we were talking about before. You embed Japan, add the same vector, you get Tokyo, so on and so forth. It's not always perfect, but the embeddings that are learned are pretty impressive. So if you're doing machine learning tasks that take word data as input, transforming into this vector space straight away is often a good way to boost performance right out of the box. And there are pre-trained models and embeddings for a ton of languages available all over the place. Okay, we made it somewhere. It's cool. Together, we've stayed together. It's great. We've had a relationship. It's lasted. It's been, good for all of us in different ways. Yeah. So at the end of part 4, like, what did we talk about? What did we talk about in part 4? We were talking about unsupervised learning, in particular with linear latent factor models, where we wrote down a loss function that allowed us to take our given data X and write it as a matrix factorization model with latent Z and W, where we identified W as the latent factors, the bases, whatever, and then the weights or embeddings or the features or whatever Zs that when combined with the learned features W or latent factors W give rise to a lower dimensional representation of each data item X. And there were tons of applications for this. We specifically focused on dimensionality reduction, features for linear models, and visualization, right? And a little bit in the end with recommender systems when we talked about filling in missing entries, right? And I tried to stress throughout, because it's going to come back to haunt us now, that although we were looking at visualization a lot of the time, really what we should be thinking about doing is learning features for later use in some kind of machine learning application. So we did PCA, we got a couple of latent dimensions, and those were supposed to be good in some sort of a way, and we used those in some subsequent classifier. We did T-SNE, and then we did classification in a nicely delineated space. In particular, we talked about principal component analysis, and highlighted the sort of canonical classical version of PCA is the one that ensures orthogonal factors and fits them sequentially. We just basically said, use SVD for this, go take another course if you care. Then we talked about non-negative matrix factorization, which is a different, it's a different setup, right?
Did we flip Z and W at some point? I don't think so.
No, I don't think so. Nope. Nira, yeah, no, we've managed to stay consistent. It's the best thing about these slides. Yep, that's still true. Zi is the part weights, for example, Xi, how much of each part W to use. Yeah. Oops. Okay, great. Yeah, great. So non-negative matrix factorization, we talked about basically, putting non-negative constraints on that gave rise to sparse factors that added together in part-like ways. We said you could minimize such an objective using projected gradient. And then we talked about lots and lots of different matrix factorization models with different regularizers, different loss functions, dealing with missing values. We did not do this, that's totally fine. Yeah. So you get sparse coding, or you get robust PCA, or when we're doing recommender systems, we can deal with situations where some of the entries of X were missing. Okay, so cool. Then we talked about MDS, which is a non-parametric latent factor model, and there we just try to match distances similar, in the high dimensional space and low dimensional space. The main problem with like classical MDS is crowding. So we talked about reweighting the cost function in an intelligent way, weighting by the distance in the higher dimensional space. That gave rise to salmon mapping. Then we talked about isomap, which used geodesic distances instead, Dijkstra's algorithm, that sort of thing. And then we talked about T-SNE and word2vec. Okay, cool. We made it somewhere. Okay, so what was the course? Okay, so we did supervised learning in the beginning. We said, okay, you have input output pairs xi, yi, and we're going to use those to learn some parameters w, some model. Okay, and we talked about different kinds of models, but yeah, we focused a little bit on linear regression, right? Then we said, okay, if we want our regression models to be really powerful, we should say, for instance, increase the size of the number of features Z. We'll use a polynomial basis or some infinite dimensional basis or whatever, right? So we want to learn some different parameters V in this different basis Z with the same target, right? And then in this last section, we talked about latent factor models where we learn parameters W that give rise to the basis, but we do it without Y. We don't have any Y, we just are given the data. And this is, think eigenfaces. We were given a bunch of face pictures and we went off and we learned a representation for those that then hopefully would be useful later on. I hinted, although we didn't actually do it, I hinted that you could use these new features as part of some later on supervised learning task. And that's quite often what people still do and did, right? So you learn based on the change of basis and a target Y. So neural networks, sorry, it's very straightforward. Neural networks basically simultaneously and jointly learn W and V based on having X and Y. Okay, so our parameters W here, and we'll go through these in a little bit more detail in a little bit. Each, I guess, row of W is a vector which relates all of the inputs X to one dimension of Z. And there's, K different rows of W, and then you have Z, and then you have Z for every, Z is, I guess, N by K by N by K, or K by N, doesn't really matter. And then you have a K dimensional V, which takes all of the Zs and transforms them into your output, okay? So by doing this, by jointly learning W and V based on our input-output pairs X and Y, the point is that whatever basis we learn, is not learned independently, right? You could learn a basis that is actually not good for the task that you want to, for the task that you actually want to accomplish, like distinguishing between payment and I, like if the unsupervised feature extractor, if the unsupervised latent factor model only produced, male and good looking and athletic and, intelligent as features, it wouldn't do a very good job of distinguishing us, but and beard, presence of beard or not, but white hair and old versus young, those are really important features to learn. And if you learn end to end, the features that you learn are likely to be features for that are good for the classification task. Okay, so this is, I think, probably my favorite slide of the entirety of all slides in the entire course. So enjoy it. It's a thing of beauty, right? So part one of the course is I have some features and I want to do some sort of regression or classification to get my output Y. Okay, that's it, right? Part two of the course is, okay, let's do some clustering or some sort of unsupervised learning, mostly clustering in that particular case, like what is the group of X? So we're going to produce a very, very low dimensional, like usually one-dimensional representation of the data. Think again, k-means, right? So we take all the data points and we produce a class label for each one of them in an unsupervised way. You can think of this as like a poor person's version of part four of the course. Part three, we say, okay, we're in the med school or we're in the sciences or we're putting things into an IEEE conference. And we say, okay, I'm really smart, so I'm going to take my data X and I'm going to produce features that are important. X1 times X3 divided by XD to the power of X squared happens to be important for science, and I'm going to make that my first feature Z, right? Great. And by carefully building features, or what we talked about in this course is we don't know anything about the problem domain, so let's just make polynomial bases or radial bases, function bases, or kernel methods, or so on and so forth, where we have some very, very richly expressive family of features that we use for our classification or classifier or regressor. Part four says, okay, forget the Ys. Maybe I don't have Ys. Maybe I just have pictures of faces and I want to make parts or pictures of digits and I want to build a latent factor representation of said data. What are the parts of X, right? And then afterwards we sort of say, okay, well, if I do PCA in these images and then I plug those features in, probably we'll do okay on the task because these features are naturally arising. They represent the actual natural structure of the data. Cool, maybe, okay, yeah. The point is these two things are trained separately, totally separately. You find some features and then you take those features and you stuff them into your favorite supervised learning model. Okay? What we're going to talk about now, neural networks leading to deep neural networks, and you can probably, as we go along, decide when you understand what deep neural networks are. The very simple idea is that you learn the features and the classifier, which means you learn the weights of the latent factor model and the weights of the classifier or regressor at the same time. End of story. And in fact, we could probably, for most of you, given what you've done and learned,
in part 3 and 4 is that we use algorithm like PCA to find our basis and stuff manually doing it.
So in part 4, we really didn't, in part 4, we did not do this at all. All we did was this, right? And then we said we could use those later, right? So indeed, in part 3, we did change of basis explicitly within a regression or classification context. Part 4, we really just did let's go find parts or latent factor representations of data with the hope that they will be useful and just asserting that they are often useful. now is the first time that we're asserting that if you stick them together, then good things happen. But we're going to go one step further and say, well, we're just going to build a unified objective and learn everything all at once. So it's like PCA to find the relevant features and then training a supervised model off of those chosen features. That was phrased as a question, but it's absolutely right. So is latent factor model with predictions tacked on a neural network? Pretty much. Is there a distinction between the features and the weights in the neural network? The weights in the neural network are going to be these guys, the things that go between the X's and the Z's. That's going to be our W matrix. And then there's some weights that go from the Z's and to the Y's. Those are more weights. They're the linear model weights or whatever. And these are all going to be parameters. And we'll go into this in more detail, but yeah, but so basically I can already tell from the comments, unfortunately, these are fortunately or unfortunately, either one, no, these are the standard group of commenters. And I know there's more people in the course than this, and some people don't even watch during the course time. So pretty much almost you could go off and just do it now, right? You say, okay, I know how to build a loss function for whatever my thing is, right? Whether it's classification or regression. I know how to take partial derivatives and take gradients, and I know how to do stochastic gradient descent. And pretty much, not quite, no, there's a couple of little details, pretty much you're there. So that's it. So in some sense, we could actually take a vote and just say, should we stop the course now? Because we're done, right? But there's a couple of little details and some hand wavy fun pictures to look at. So we'll do some of that. So it's actually, the nice thing is that, you know, compared to kernel methods or something like that, deep learning is much, much simpler. And that's part of its appeal, right? So when we're doing neural networks and deep neural networks, right, we're going to have our standard usual supervised learning notation where we have the matrix X, which is n by d, right? In examples, d-dimensional X's, and our labels, which could be real valued for regression or categorical or whatever binary for classification. We have n of those, so an n by 1 vector. We have our latent features. Those are going to be n by k, so k-dimensional latent features. And now we have two sets of parameters, although I will often just refer to this as the set of parameters or the parameters, right? Which are V, the final linear layer weights, and W, which are the feature transformation weights. So again, you know, when you go from X, which is going to be D by 1, right? The first row of W are all of these weights. The second row of W are all of these weights. Sorry. I do that every single time. Literally every single time. It's completely ridiculous. Erase. Oh, don't erase the whole thing. Erase that. Nobody ever calls me on that either. It's really bad. The first row of W are those weights, i.e. this one, this one, this one, this one. And the second row of W is all of these weights, and so on and so forth. Okay. Third row, all of these weights. Fourth row, all of those weights. Okay. Cool. It's really easy to see what's going on here because now Z is going to be a nice K by 1 dimensional thing, right? And the K dimensional vector is just this right here. And when you dot product it with this V, you get your output for Y. Okay. Fine. Yeah. So that even works out notationally here. So the obvious thing, which has just been, and this is one of the key details about neural networking or deep neural networking or whatever, right? So one of the key differences will arise here. So the obvious thing to do is to take a linear latent factor model like PCA and combine it with a linear regression or classification model, okay? So we use features from a latent factor model. So we just say Zi is just WXI, just like I just drew in the last one. And we make predictions using a linear layer V transpose Zi, YI, okay? All right, anybody want to, Payman, is this a good idea or a bad idea? Or anybody in the audience?
Uh, it's not a bad idea, but we could do it better, I guess.
Oh, it's not a bad idea. Okay. Well, okay. Let's see. Let's see if the students can beat payment. No flipping ahead on the slides. That's cheating. I can always tell when you do it. Think about it. Let's do a little bit of math. Linear equals bad. No, linear is not bad. Linear can be really, really good, particularly if you have a very large feature space. Is this the same as polynomial basis? No, it's not the same as a polynomial basis. The text is green. The text is green, so it must be good. Yeah, no, okay. Actually, this is the first time that, sorry, this is the first time that this section did not get the answer like the last section. The last section just bang like that. Okay, so here we go. Here's the deal. All right, so let's do least squares. That's one of our losses, right? So let's just write V transpose Zi here and focus on that part. If we plug in the definition of Zi, it's just WXI. The problem is that this is just a linear model. Okay, so when you do V transpose Zi, that's V transpose WXI, and that thing is just some vector W, right? And all this is a linear model, right? Basically, it's just a linear classifier with a heck of a lot more parameters for no good reason. And, you know, what's the point? Okay. It's faster? Nope, not faster. So the point is that if you do this, then all you have, and we're talking about linear regression, right? A linear latent factor model with linear regression equals just linear regression. I mean, it's exactly this, right? It's no different, right? So we have to do something a little bit different. There has to be an extra little bit of juice here in order to make things happen. Basically, we need to make the model nonlinear. So this is a little bit close to what Tobias said, but I think he went just a little bit far with linear equals bad. Linear is not necessarily bad, but if you're looking for more than linear, then you need to come up with an architecture or computational diagram that is more expressive. Okay, so to increase flexibility, we need something to be nonlinear, and the typical and very reasonable choice is to transform the latent factors Z by some nonlinear function H. Okay, now recognize this function H is going to be a function from a vector Z to a vector Y, and usually the H is going to operate pointwise on every dimension of the vector. So the function H transforms K inputs to K outputs, and a common choice, certainly a historically common choice, is to apply the sigmoid function element-wise to the vector Z. So H of one element of Z, ZIC, is just the logistic sigmoid function applied to that value, okay? This takes a real valued Z in the range minus infinity to infinity and maps it to 0, 1, okay? And when you choose this particular form of nonlinearity, what you get is called a multilayer perceptron, or historically a neural network. Okay. Now you could ask why sigmoid, and this is going to go back to sort of when we were thinking about the loss functions for classification, right? And you can think also of neural networks, just to say the words, even though I don't have slides for it, just to say the words, you can think of neural networks as being some sort of stacked classifiers, right? So if you have a classifier of for, you know, good looking, you like take a picture of a person, you good looking, male, you know, strong, you know, athletic, has beard, so on and so forth, white hair. If you have a classifier for each of these things and you then learn a stacked classifier on top of it, the stacked classifier would be able to distinguish Payman and I on those bases, with binary features that had been pre-trained via some other source of labeling, right? So if we consider setting H to be basically to define binary features, just like I just described, where the nonlinear transformation is literally just the step function of 1 if, you know, zic is greater than 0 or and 0 otherwise, then you can think about each nonlinearly transformed dimension of Z as being a binary feature. Either you have this part or you don't have it, right? And that's kind of actually what we were getting at with this like parts-based stuff way back when we were talking about it. Basically, we can make 2 to the k objects by identifying all the different part combinations that could be or are in the final object, arising from however many of these parts get turned on or off, right?
Why does that make Nolan for good? Because we discarded the individual prediction model in favor of multi-class classifier before.
Okay, so we're just remember we're in the space of going from xi to yi. Okay, so and we've said that if we do a linear model, a linear latent factor model, and a linear model, we get linear regression back. Okay, so that doesn't really make any sense, right? And we said that we want to put some sort of nonlinearity in. And what we're trying to do is sort of give you some feeling for why what this nonlinearity does, beyond just saying it expands the feature, it expands the function space that you can approximate in the expressivity, right? And it is deeply related to the idea of making all of the Zs be individual classifiers. But like it's the point that you're raising here is if this is, you know, Z1, C, Z2, C, whatever, I guess that's not what it is. ZI1, ZI2, ZI3, so on and so forth. You don't have these labels. You can't think about stacking or not stacking. This is not what we're talking about, right? You don't have these. These are latent, right? All you have are the Y's and the X's. Okay. So the fact that we use some nonlinearity means that you can, in your head anyway, think about what's happening as there being some sort of parts-based representation, some sort of factorial representation being represented in the inner layers, now what we're talking about, one layer, in the latent layer, the hidden layer of the neuron. Right? The problem is that like hard parts-based step function is not differentiable and is discontinuous, really discontinuous. And, you know, just to point it out, like we talked about before, there's really no gradient signal here at all. There's no learning signal anyway, right?
What if you have a non-binary feature?
Okay, y'all, come on. We're establishing intuition. We don't know what these features are going to be, right? We're building up a mathematical representation of a regression or classification function that happens to use a linear layer and then a nonlinearity, right? If anybody tells you they know what's going on inside of a neural network, they're smoking crack. Nobody knows, right? But intuitively, this is not an unreasonable way of thinking about what's going on, particularly with sigmoid activations, right? And you know, to relate to the comment that I just reacted to, you know, if you have a non-binary feature, well, you know, this. Okay, if, you know, HZI, right, you can think of, if you push it through a sigmoid, you can think about this is the probability that this feature is there or not, right? Okay, so basically, first step, we have this HZI, we can think about that as what we want the parts to be. If we push it through a sigmoid, then we can think of that as a smooth approximation to the stepwise part availability or not, but for the same argument that we used to interpret this as the probability in a logistic regressor, you can think about this as being the probability that a part is there or something like that, right? Also, in terms of theory, which we're not going to go into here, but you can look it up if you want to, if you take a version of a single layer neural network with in the limit of the number of hidden units, the dimension of Z going to infinity with sigmoidal activations, then that architecture, this neural net, you can prove that it is a universal approximator in the sense that so long as k grows appropriately within, you can model any continuous function between x and y, okay? And that's a pretty powerful theoretical statement, if somewhat irrelevant to modern practice now. Okay, so supervised learning, here's the roadmap. You can hand engineer features, right? You need some sort of domain knowledge that can be hard to get that. You have to pay somebody for it. You build a basis and you use that in your regressor, right? Or you do like what we've been talking about in section 4, you learn a latent factor model, right? And then you use those latent features in a supervised model. The problem is that a good representation of X, a good reconstruction of X, might again be really bad for predicting the label. We don't really know for sure, right? Okay, so simple combination, learn, W and W or V and W together. That's a really nice idea, but it basically, if you don't introduce the nonlinearities, it's still a linear model. That extra nonlinear transformation makes it different, right? It makes it more powerful, it makes it a neural network, okay? Universal function approximator if Z grows appropriately in dimension and in, fine. Okay, now you can ask, why are these things called neural networks? Does this make any sense? Where did this come from? So on and so forth. And here's some very hand wavy, very loose, very approximate, almost so approximate as to be embarrassing talk about why people call these things neural networks. Okay, so here's a very cartoonish view of a typical neuron where effectively we have the inputs, which are received on the dendritic side, and the outputs, which are output on the axonal projection side. Okay, so I got a question from Akeem. So technically speaking, H does not have to be a sigmoid. No, if you're familiar with rectified linear units, that's one of the favorite, I would say, one of the two factors that has led to modern deep learning, two major factors that have led to modern deep learning, that and lots of computers, three majors, lots of data, lots of computers, and rectified nonlinear, rectified linear units, yeah. Yeah, sigmoid activations are still used, but not that often, and usually often in only one or two layers or something like that, yeah. In particular, if you want to transform into probability space for whatever reason, that's there. It's still very much used for that. Okay, so we've got this typical neuron inputs, dendrite, outputs, axon, it's a nucleus. There's some insulation, and so that signals can propagate this way through the neuron. Okay, neuron has many dendrites, which take some sort of input signal. Pyramidal cells in particular, I'm not going to go into neurophysiology, but there are lots of different kinds of neurons, and don't, all the neuroscientists out there, please don't, cast stones. Pyramidal cells have a single axon, which on which an output signal is transmitted along the axon to its outputs. Okay. With the right input to the dendrites, so we're going to see the X's come in here at some point, X1, X2, Xi2, whatever, I1. With the correct input to the dendrites and the correct level of animal evolutionary development, because, like, for instance, C. elegans does not actually spike, and other nervous systems don't actually have action potentials, but in mammals, for instance, neurons upon receipt of a certain level of stimulation will rapidly depolarize, and this electrical signal, which is a change in voltage between the inside and outside of the cell, when a certain threshold is reached, basically adding up or computing somehow on the inputs, an action potential, basically a change in voltage is propagated along the axon, and then it communicates out through the through the synaptic junctions at the end of the axon. into the next layer of cells. So the action potential that propagates along the axon is kind of like a binary signal, very like a binary signal, okay? So just to do this a little bit more in more detail, here we have the dendrites, and here are the various dimensions of the input signal. So this is the mapping that, if you're going to talk about neurons and deep learning and that sort of thing, this is the mapping you should have in your head. So you have inputs coming in, then the neuron computes some sort of internal activation, right? ZIC. Okay, so there's going to, this basically is the Cth neuron that we're looking at here, computed on the ith input, right? And the weights on this particular neuron correspond to basically the weightings of each of these inputs. You can think of them as the synaptic strengths on the dendrite here and the connections to the previous neuron, okay? Computes this inner product, and then there's some sort of nonlinear activation, i.e. the spike, right? If ZIC is greater than or equal to 0, it sends something down the neuron, it sends a signal, and then it emits something along it emits neurotransmitters to communicate with neurons further along the line. We approximate this binary signal with a sigmoid, that's fine. And we assume that it's propagated perfectly. Great. So the inputs, so again, there's going to be, ZI2, I guess that's ZI3. There's going to be a neuron just like this copied up here, ZI2, there's going to be another copy here, so on and so forth. So there's going to be K different copies of some neural structure like this, all receiving the X input. The nonlinear transformation of their outputs gets propagated. So you get H of Zi on the dendrites of the next neuron. That neuron computes the inner product with the vector V. It then sends the signal Y hat along its axon, okay? So that's the mapping you should have on it. Stacking neurons, yeah. So this is feed forward neural processing. There's a whole bunch of ways of talking about it. So Y neural network, again, the dendrites for the ZIK neuron are receiving all of the X values, right? That neuron aggregates signals with an inner product, right? It sends a nonlinearly activated signal along its axon. The synapse between the YI neuron gets all K dimensions of Z and then aggregates and then nonlinearly transforms that often out to its output. So it doesn't necessarily need to nonlinearly transform it. So it takes a nonlinearly transformed version of the weighted inputs and then produces an output. You can do all sorts of stuff. You can keep stacking and so on and so forth.
Did machine learning researchers actively try to replicate biology, or did this happen there?
Oh, this is a really... okay, great. Okay, lots of stuff coming in right here. Great. So this first question is a really good question, and I haven't cashed in enough of my historical context to really say. But very historic, even fundamental neuroanatomy until very recently has been more or less totally unknown. So pyramidal cell networks, what's the guy's name? Golgi? No, Golgi? Who's the staining guy? Golgi, I think. Anyway, so the idea that networks like this, or this kind of circuit diagram is indicative of what's going on in the brain has been around for a while. So they definitely knew about this. And yes, when people were studying connectionist kinds of architectures and thinking about how artificial neural networks or how we should build thinking machines, they were definitely inspired by very early results in neuroanatomy. Turns out that those are basically grossly inaccurate and inadequate to describe what's going on. But then, then a theory was built around this, and we've gone from there. Amit, yes, you should definitely think of X as having a bias column of ones. That's just sort of implicit in this, absolutely. Cahal, thank you very much. Yes, thank you. That's exactly right. I should remember that from all of my computational neuroscience and neuroscience training, and the fact that I've actually seen his original manuscripts in person at the Wellcome Trust in London, which is rather embarrassing. But yes, if you look at his stained neural networks, basically only picked up on pyramidal cells, and that gave rise to this sort of connectionist picture of the relatively simplistic connectionist picture. If you want to see stuff that really will blow your absolute mind, you should go look at Bobby Kasturi's work. He's now at Argonne National Lab, who's arguably the foremost neuroanatomist in the world now, out of Harvard lab. Who that guy would really be pissed off because he was his student. Shoot, I forget his name. Anyway, the actual neural networks are totally insane. Anyway. Do we have time? I might pull that up on my other machine. We won't have time since I'm running late again. Anyway, so artificial neural networks, X is the measurement of the world, Z is the internal representation. It's latent, Y is the output. Real neural networks are way more complicated. In particular, there's spike time dependent plasticity theories. There's rate coding theories. Rate coding seems to be the one that's dominant. And if you think about what ReLU neural networks are doing, they're actually basically simulating a rate coded neural network integrated over spike times. Artificial neural networks generally, unless designed to do so, don't reflect the sparsity seen in real action potentials. It's not clear that an inner product is a plus a nonlinearity is a really faithful approximation of what's actually being computed inside of a neuron. There's a lot of structure in the brain. We know that synapses grow and disappear. In fact, there is even some evidence that neurons themselves grow and disappear, although that's questionable still. And there are definitely different types of neurotransmitters. There's different types of cells, all sorts of stuff. Anyway, so what's deep learning? Well, you've pretty much probably guessed it at this point. It's just rinse and repeat. So, here's our first neural network. Now we stack on another neural network, and voila, we're done. Repeat ad infinitum. As it turns out, the snarky comment on the chat channel, the more layers, the deeper the learning, turns out kind of to be true. So understanding why is at the very forefront of modern theoretical machine learning, one area. And Dougal Sutherland, who's coming to be faculty, should be coming in January. If you're curious, you should sign up for his courses because he's been working on deep learning theory at sort of, I'd say, the modern hotbed of deep learning theory research, the University of Chicago, TTI, the Toyota Technical Institute at the University of Chicago, with Nadia Shribro. And they've published a bunch of really crazy stuff. Okay, anyway, so the idea is, as you go deeper, like one idea about what's going on is that, if the first layer recognizes simple parts, then the next layer you can think of, particularly if you think of sigmoid activations, you can think of them as recognizing combinations of parts, and then combinations of parts, and so on and so forth. Do we have to worry about overfitting when we have more layers? Oh, the $6 million question. Traditionally, the answer to that would be yes. Traditionally, the answer would be yes. Based on everything that we've talked about in the course, the answer should be yes. And there are lots, and the reality is that yes, you can overfit. But in practice, what we've found in deep learning is that you overfit much less than you should. And that is, again, an area of active research to try to understand why that is so. It turns out that the combination of stochastic gradient descent and overparameterized models is very special. In the example network here, could we go backwards and construct the most ideal digit representation? But okay, Alan, this is a spectacularly good idea, and we don't actually, I don't think we covered in this. Maybe we do. I don't remember. I have to think about what the slides are for Friday. to answer that question, very much foreshadowing. Yes, you can always in a deep neural network take a gradient or a derivative with respect to either the output or the input or the parameters. Okay, so if you fix the output and you fix the parameters and you take a derivative with respect to the input, you can always try to find the sort of the optimal 8 that gives rise to the highest activation for 8 or something like that. Yes, absolutely. What's the difference between using stochastic gradient descent and mini-batch stochastic gradient descent in deep neural networks? That's a little bit too soon for that, but the answer is either you compute with a mini-batch or you compute with a single example. And yeah, it's basically speed and GPU use. So you should choose the largest mini-batch you can and the largest learning rate you can. Anyway, yeah, all right, cool. So pretty much we'll just blaze through the rest because it's really straightforward, right? So you've got your linear model, then you've got your neural network with one hidden layer here, right? There's Z1, here's the nonlinearity. You got 2 hidden layers. There's Z1, the nonlinearity. There's Z2 and the nonlinearity. And guess what? Now you've got a neural network with 3 hidden layers. Same story over. Here's one with 4 hidden layers. We introduce and use, and I think this is the only place in the world where this is used. We have this nice symbol. Maybe I've seen it in one other paper. We have this nice symbol, which is basically just the which is just linear composition of functions. So if you say that the function is HWL of X, and you do that 3 times with L being indexed by that, then you have a 3-layer deep neural network, okay? Cool. I'll answer the question in just a second. I just want to buzz through this because the history is kind of interesting. 50s and 60s, there was a huge amount of excitement. This is when people were like, oh, we can build circuits that look like this. Awesome. The perceptron that we're talking about, right? It's the embryo of an electronic computer that the Navy expects to be able to walk, talk, see, write, reproduce itself, and be conscious of its existence, right? You've got your inputs, you've got some potentiometers that you can set or automatically set, you've got an output, and so on and so forth. This is my kind of thing to do to my graduate students, right? Object recognition was assigned to students as a summer project. It'd be no problem, easy, no issue at all. And then basically they figured out that things didn't work quite like they thought they would because everything was linear, right? Whoops, missed something. Took a little while to figure that out. People continued working on this though, like there was a little bit of a dead period in AI/ML research. Connectionism was stayed strong though. And when it connected units to simple units, parallel computation, distributed representation, and you started to see some results where the data sizes weren't too large and you could actually compute. This is when the universal approximation theory was built, and like recognizing postal digits and that sort of stuff. And in the 90s and in the aughties, there was a huge drop in popularity because it basically was impossible to get multi-layer models working correctly. This is because we didn't have enough compute and we didn't use ReLUs basically. And during this time, this is when we got logistic regression and support vector machines and kernels and so on and so forth. And if you look at Alex Smola at Amazon or Bernard Chilkoff at MPI, they've got hundreds and hundreds of thousands of citations, and this stuff still works. It's super powerful. And, in fact, in some sense, we're very lucky that this period happened so that we could actually develop this other theory. There are tons of internet successes using these sort of simpler logistic regression SVM style models, stuff that we've covered in the course. And for people like me who trained during this period, we spent a lot of time doing statistics or numerical optimization and that sort of thing. And in the late 2000s, then deep learning started to come to the fore again because we got faster computers and we started thinking about smarter activation functions. The push was led here in Canada by 3 fellows who won the Turing Award, I guess, last year. And I'm out of time, so I won't go into it. But basically, it was the beginning of what we see now. So deep learning now, bigger data sets, huge models, parallel computing, and really very small tweaks from what we knew a long time ago. Different activation functions, stochastic gradient descent, bigger computers, and now every one of your mobile phones has stuff in it for automatic speech recognition noise canceling and so on and so forth. And computer vision was completely transformed in 2012. And now basically computer vision is deep learning only. Yeah, so there we go. Yeah, that's it for today. Yeah, so neural networks, they learn the features as well as learning the supervised learning weights. Sigmoid functions are still used, but not that much. It's really about the universal approximator theorem. But the idea of the nonlinearity was born there, and it's an important way to think about it in terms of compositions of hierarchies of parts and that sort of thing. We've like tied together a sort of wishy-washy biological motivation with deep networks. Deep networks are just neural networks with a bunch of hidden layers, and for various reasons, they empirically and theoretically can be shown to more efficiently represent some functions from X to Y. And we all know at this point that they have given rise to a whole new era of performance on a huge number of classification and other pattern recognition tasks. Okay, cool. Questions, comments?
I guess there was a question of whether the runtime be super slow.
So Jake, this is yeah, I think the comment stream after this is totally on point, right? So yes, the answer is yes. The runtime of deep learning is super slow, right? If you actually count the number of flops that are required to compute in one of these models, it's absolutely astronomical, right? It's mind-boggling. On the other hand, most of deep learning consists of a very, very small number of function types. Inner products, convolutions, which are just inner products anyway, more inner products, more matrix multiplications, matrix vector multiplications, basically all over the place, right? And if you happen to write software that means that you can compute these things in parallel for properly batched tensors or matrices, and you say, for instance, have 10,000 cores at your disposal that can do one very small operation really, really, really fast, like, for instance, GPUs, then you're good. And yes, indeed, it also means that you can develop very, very specialized hardware that really, really focuses on the kinds of computations done in deep learning models. And on those specialized pieces of hardware, you can, yeah, the flops are being done. they're getting counted, but they're just able to be done really, really fast because effectively you have 10,000 way parallelism on your machine and very, very nice numerical linear algebra packages that parallelize with near perfect efficiency on that kind of hardware. And then you can go even further to tensor processing units, which is basically the same thing. But yeah, I mean, there's 6 ways to Sunday you can build hardware to do deep learning stuff. Other questions, comments? Are there other courses at UBC about deep learning? Yeah, there's, I think probably the closest to a pure deep learning course that we have is Leonid Segal's, because computer vision now is so dominated by deep learning that you could basically say the computer vision, the 400 level computer vision course is a deep learning course. I mean, you get it in various flavors and a bunch of stuff. My prog course has a ton of deep learning in it. But the reality is that modulo a few tricks and definitely architectures and that sort of thing, there isn't a huge amount more to it than stochastic gradient descent and you know, various activations and various layerings. So it's really not that bad. How do you determine the optimal depth for a deep neural network? So it's like the same question as how do you determine the optimal width for various layers in a neural network? How do you obtain the correct computational diagram? Mostly it's graduate student descent in the space of architectures, but really it's a hyperparameter search of some kind. Just a hyperparameter, so you can do cross validation or some other kind of other kind of model selection criteria. There are there is work called neural architecture search. Look up Otto Karas if you're interested. That explores how to automatically learn the structure of the neural network as well as the parameters for that structure. Of course, it's non-differentiable, so you have to do some sort of greedy optimization thing, basically. Then maybe it's his graduate course. Sorry, if it's true that the 400 level vision course still is the old school. I think Leon changed the course either this term or last term. So. This is a really, really good question. So a lot of the research, I'd say 50% of the research at this point is just showing what you can do in various applications. Some fraction in the last maybe 2 or 3 years is about deep learning theory, trying to explain what's going on. And some very small fractions about like doing architecture search. And there are a steady, there's a steady stream of little tricks that are very, very important. And I think that right now the deep learning, machine learning literature is like going through it is kind of like looking through a big haystack for the few needles that really matter. Dropout is pretty important. Batch norm is pretty norm. A few generic architectures, LSTMs, basically HMMs, variational RNNs, basically HMMs, convolutional neural networks, fine. The architecture search thing is important, right? Architecture does matter. It turns out it's maybe the most important thing. But it's not clear how to proceed other than to just try a bunch of stuff. And a lot of papers are just, here's a new architecture and this is how it does. And is that interesting? It depends. Scientifically, maybe not, but that's how science works. It works in ebbs and spurts, right? We try a bunch of stuff and then somebody figures out some general principle for explaining why we're seeing what we're seeing. And that's happening right now in deep learning theory with stochastic gradient descent and trying to figure out like what, the lottery ticket hypothesis over parameterization. Why are there so many good local minima? Why does SGD find those good local minima? Why don't neural networks, overfit as much as they should? There's a whole bunch of really interesting work there. And there's a whole bunch of interesting work in combining deep neural networks with probabilistic methods. And that's how you would describe my research, basically. Abstract question: if this is more or less figured out, what do you think is the next big thing? I've been banking for my entire career on properly calibrated uncertainty and propagation of uncertainty throughout calculation. So in the sort of big sense, even though I didn't coin this term and I don't work directly in this space, like Bayesian deep learning is probably pretty important. More and more people are figuring out that remains interesting and important. And I think neural architecture search is annoyingly important. But that really is combinatorial optimization, right? Or mixed discrete continuous optimization. my monitor just blanked out. So is that where the high time complexity to? In the diagrams that put up earlier, there were edges between every pair of nodes and a layer. Is that where the high time complexity of DNNs come from? The high time complexity comes from the fact that yes, you know, you're doing a latent factor model basically. If you think of a deep neural network as just a stacked multi-layer perceptron, is basically what we've been looking at right now. Then there is at the end of the day, the z vector for every x vector is a big matrix multiply. And if the dimension of Z is 5,000, and you have, you know, 1,000 dimensional latent feature vector, and you have 10 layers of that, and you've got 1,000 by 1,000 multiply, right? A matrix multiply with, you know, a whole bunch of data items, and you've got a million floating point operations just to do one multiply, and that's one layer, right? So it adds up very quickly. So couldn't we use some method to create more sparse layers to improve this? So it turns out that yes, this is true. And if you want to look at this, this is kind of like the lottery ticket hypothesis, or what do they call this? It's not distillation. Distillation is something else. When you do the neural network compression and you throw, I mean, distillation is one way you can do it. But yes, there are greedy methods for throwing away edges in neural networks and preserving performance. Yeah. I'm an undergrad, very interested in research here, but save for the class, I don't have a lot of experience in machine learning. What do other ML faculty look for when taking undergrads for research? Would doing more Kaggle competitions help? That's a really good question. It's the canonical question. So one thing that you'll find is the machine learning faculty here are just completely, totally overworked to an extent that is very hard to describe. Yeah, it's a little bit of a chicken and egg problem. More Kaggle competitions for research generally does not help, except that it helps you with your tooling. So I think no. Okay, great. Okay, this is good for anybody who's listening. Please understand. Undergraduate research assistants or these sorts of things are not more help; they're more work, because the goal is to provide, you know, like the value. This is one of the things that when I was an undergrad, I was so pissed because I would go in and be like, "I'm going to give you free labor. What's wrong? I'm super awesome." And I didn't understand actually that the labor that I was providing was not actually valuable because I needed so much training, even though I was actually pretty awesome as an undergrad. And that's not to say that that won't be true for some of you, but in large part, the skill sets that you need to show are actually unbelievably writing. Being able to write clearly is super, super important. Being able to do mathematical notation really, really well is really, really important. To be able to frame problems, super important as well, is really, really important. Being familiar with the modern research literature is super important. And, you know, being able, you know, it's expected of any graduate student or anybody who works in a research setting that they know how to program, they know how to do their own tool chains, they know how to you know, do their own analyses, they know how to do math, they know how to do all of it. So like like doing stuff to improve that is great. That's kind of where you are in the stage. Like all of you are going to be more proficient programmers than me. You'll be faster. You'll do PyCharm faster than me. You'll do weights and biases better than me, so on and so forth. But the thing that would be really attractive is if somebody came in and said, okay, and if you really want to work with any of us, the thing you really need to do is you need to go read our last 5 or 10 research papers, really understand them, and come in and say, I think you should be doing this. This, I think, is an interesting problem, and I'm going to do this. You want me to do it? Can I work with one of your grad students to do it, or whatever? So the best thing to do is to identify research. That's always the case, is identify a research problem, and ideally find a grad student in the lab that you can kind of glom onto. So I have some undergrads that come to my group meetings. They participate, they read, and I certainly will take some from this year's crop of 340, but it's a very small number. And that will be true for everybody else. So, yeah, the best way is go read a bunch of research papers, find out what's actually interesting, and you'll see that there's still a very large gap that you have to fill somehow, but you can fill that with self-study and these sorts of things. I don't mean that to be discouraging, by the way. I mean that to be encouraging. Basically, you got to eventually at some point you got to do what all of us do. You know, when we decide to become machine learning researcher people, we pick up a book like this on our own and we do every single gosh darn problem in the book. And then you can come in and you're like, okay, I know machine learning, right? Great. Then you're ready. And then the sooner you do it, the better. This holiday season, I mean, you can't go anywhere anyway. Just pick up Bishop. Brief thoughts on studying math versus stats. In terms of my respect for is measure theory worth it? Yes, it's worth it. Yeah, it's totally worth it. Is it worth it in the sense that if you become a machine learning researcher or practitioner, you're going to need it? No. In order to be able to read papers and operate at the very fringes of research, in particular probabilistic methods, yes, you will definitely need it. And I think it's better to get it sooner rather than later. Payman will probably think something different, but he's not in my group, so yet. Yeah, I mean, fundamentals are important. Real analysis, super important. Measure theory, super important. You know, frequentist statistics, maybe not so important. Bayesian stats, really, really important. Probability as a subject, very important. Yeah. Cool. All right. Lovely. Thank you all for your time and attention. Sorry for running a little bit late.